Hello, this is Sadbir. The topic of our discussion in this video is sequence. In this video tutorial, we will cover the two concepts of sequence. One will be the definition of sequence, and the second will be epsilon and definition of the convergence of a sequence. Here is the definition of the sequence. A sequence is a function whose domain is set of natural number whose domain is set of natural number. In other words, sequence is a function f whose domain is set of natural number, and it may map the set of natural number into real number r. For example, f of n is a sequence, it's 1 over n. It takes all the natural number n, which n belongs to set of natural number, and it produce real numbers. There is another example of sequence here, which is fn, which is equal to 1 over n square plus 1. This is another example of a sequence where n belong to the set of natural numbers and takes all the natural number and produce real number. The notation for a sequence, we write a subscript n is equal to basically f of n. So in short, we define the sequence as an. For example, here what will be my a1? A1 will be the value of the function fn at the point n is equal to 1. In this example, in my first example, my a1 will be 1 over 1, which is 1. And similarly, I can calculate a2, which will be 1 over 2, because I'm taking the value n is equal to 2. So these a1, a2 and a3 so on, they are called the terms of the sequence. And the term an is also has a name, and it is known as the journal term of the sequence. For the convergence of the sequence, we need the sequence, and also we need the limit of the sequence. And in calculus class, we have learned that how to compute the limit of a sequence. So you're supposed to have that two a quantity before basically we write down the definition. First, we will need what is a sequence and what is the limit. And then we say that the sequence an converges to the limit L. So this is the symbol which is we're gonna denote for convergence. So it's convergence. So we say that the sequence an converges to L if and only if it satisfies this statement. The statement is for any given real number, for any given epsilon, where epsilon is a real number and this real number is a strictly positive, there exist, or we can always find there exist n, capital N, which is a natural number, uh, so that when n is bigger than that capital N, bigger than or equal to that capital N, we have the distance between the nth term of the sequence or the journal term of the sequence and the number L, which is the limit, that is less than that epsilon. So again, this substitution say that for any, so epsilon is here an arbitrary number. So you can always find n, you can always find a natural number n, and that when you compute the journal term, which is a bigger than that capital N, the distance between the journal term and the L is less than that epsilon. So since we are choosing epsilon any real number, so we can choose as small as possible. So in other word, what we are saying that the distance between the journal term of the sequence and L is getting smaller when n is getting larger. So let me give you the picture of this definition. So in order to draw a picture, I'm gonna take an example of a sequence. Let's suppose I take 1 minus 1 over minus 1 to the power n over n. And in this case, I basically know the limit of the sequence is 1. If I calculate the limit of this sequence, it will be 1. So let's plot the picture here. I'm gonna start by basically writing down the term of the sequence on the y-axis, and here I have the n. So if n is a 1 and 2 and 3, 4, 5, 6, and so on. And let's suppose this line is 2. Let's suppose this one is 1, which is the limit of the sequence, and this is a 0. So let's start plotting A1. So A1 is basically 2. So I will plot it here. What will be a A2? A2 is 1 minus 1 half, which is equal to 1 half, and it's gonna be somewhere here. And similarly, A3 is gonna be 1 plus 1 third, is going to be somewhere here. And then 1 4, A4 is going to be 1 minus 1 4, which is some slightly less than 1. So it is going to be here. Similarly, A5 is going to be here, A6 is going to be here, and so on. So as I can see that as my n is getting larger, the distance between 1 and the journal term of the sequence is getting smaller and smaller. So when I reach some number, like let's suppose 5, uh, when that's what I'm saying, when n is getting larger than 5, the distance between this a, n, and 1 is really, really small. Let me take an example, and we will show in that example that how to prove that a certain sequence is converges to its limit. Let's, for example, I have a sequence an, which is equal to 1 over n square, and the values of the L in this case is 0. So we prove, in this case, we will prove the an is converges to 0 by definition. So what basically we want to show in this case, so proof of this example will be, we want to show that for any given, for any given epsilon, for all epsilon, we can find, or there exist, this is a symbol of there exist a n which is belong to the set of natural number, such that, this is symbol of such that, so that when n is bigger than or this equal to capital N, this implies the distance between a n and 0, a n and L, which is a 0, is less than epsilon. That is, what is a n? A is a 1 over n square, and what is L? L is a 0. This is a less than epsilon. This is what we need to show basically, that there exists. So this is what we need to prove. The existence of n is the essentially for this proof, that we need to prove that for if I choose any epsilon, there is always a exist. So I need to find the existence of n, so that when the little n is bigger than that capital N, this distance, the distance between the journal term of the sequence and the limit is less than epsilon. So let's prove. So first, basically, all we need to show is show the existence of n. So first we're gonna find n, or we're gonna show that n exists. So here is some scratch work. So we will start from 1 over n square, where I basically left out minus 0, less than epsilon. In other words, this is a 1 over n square is less than epsilon, because if you take 0, it's just will be 1 over n square. Since n is a natural number, this is a positive number, so I can just remove the absolute value and I have this, because n belongs to the set of natural number. And this, if I calculate the n, or I take the reciprocal of this inequality, I will get n square is strictly greater than epsilon, and from here I can get n is strictly greater than 1 over epsilon here, and here I can get the n is strictly greater than 1 over square root of epsilon, because n is a set of natural numbers, so you don't need a plus minus sign, because of the positivity of n. Now this is the person of interest for us. So for 1 over square root of epsilon, this is a real number. So that's because epsilon is a positive. So 1 over square root of epsilon must be a real number. So for that real number, by Archimedean property, so Archimedean property says that for any real number, there exists always a natural number. So there exists a natural number. I'm going to call that natural number basically the capital N, which I need, belong to the set of natural numbers, so that that natural number N is strictly greater than the real number, the given real number, which is a 1 over square root of epsilon. So this is the Archimedean properties gives us. The Archimedean property gives the for this real number, so which this real number I get from this scratch work. The Archimedean property for corresponding to this real number, there exists that n, which is strictly bigger than that 1 over square root of n. So now I'm gonna basically go back to my proof. My proof is basically I need to prove that for this number n, so for n strictly greater than or equal to that capital N, I need to compute, basically I need to prove that this is less than is equal to epsilon. So I'm going to say 1 over n square minus 0. I'm going to compute this. Because since n is strictly greater than is equal to epsilon, it means 1 over n square is going to be strictly less than 1 over capital N square, because if I take the reciprocal on a square on both sides, so this inequality will hold. So since here n is bigger than square root of 1 over epsilon, so this implies also 1 over n is less than square root of epsilon, and that if I square on both sides, this implies also 1 over n square is less than epsilon. So this is less than epsilon. So that proves basically, now this finishes the proof that whenever I have n is greater than is equal to n, this always implies that n is, which is exist from the Archimedean property, a n minus l is less than epsilon. So this proves basically the sequence an is converges to l. What is our an? Is a 1 over n square. That sequence is converges to 0. So this complete the proof of these examples that for any given epsilon, so whenever I choose a epsilon positive, there always exists a natural number n. There always exists a natural number n, so that when n is bigger than n, so this distance is less than epsilon. And here very carefully I calculate what that capital N will be by using the Archimedean property. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, I have this is important result that if a sequence is converges to a limit, that limit must be unique. Or in other words, let's suppose we have a sequence an which is a converges to the limit L1, and this the same sequence converges to another limit, which is, let's suppose, called L2. This implies we need to show that this L1 in fact is equal to L2. So these L1 and L2 are same. In order to prove this theorem, I need a little lemma. So let me state and prove that lemma. So lemma say that when we say the two real numbers are equal, so for A and B belong to the set of real number, we say A is equal to B if and only if for any epsilon positive, it follows A minus B is less than epsilon. So this is our lemma, that if the two real numbers are equal, their distance will be always, you can make their distance always less than to any given real number epsilon. Or you other words say this epsilon intuitively is really small. If the two number are equal, their distance is small. If the distance between the two real numbers are really small for any given epsilon, then we will see that these two numbers are equal. I will prove the reverse conclusion of this theorem, because if the other conclusion is basically the obvious, that if the two real numbers are equal, so you can always take epsilon any positive real number, so which will satisfy this inequality, because the distance between these two will be always equal to 0. So I will prove the reverse inclusion, which I need to use in my theorem. So I'm going to prove it by contradictions. So let's suppose this hold. Suppose epsilon for all epsilon greater than 0 implies A minus B is always less than, but A is not equal to B. I'm going to assume that A is not equal to B. If A is not is equal to B, then I'm going to take this epsilon 0, A minus B, which is the difference between these two real numbers. If they are not equal, it means the distance between there must be strictly positive. So now I'm going to use this statement because this is a given. For any epsilon, we have this statement. So this implies for this epsilon, so for epsilon 0, which is a positive, this will follow that A minus B will be strictly less than epsilon 0. And that epsilon 0 is nothing but this is equal to A minus B. What this improve? This implies A minus B is strictly less than A minus B, which is an absurd statement, which is a contradiction, which is contradiction. So this proves that when the two real number A and B are equal, then you can always find an epsilon. For any epsilon, their distance will be less than epsilon. And if this is a true, then these two real numbers will be equal. Now let me give you the proof of our main theorem. So in the main theorems we have given, so we have AN is converges to L1. So if AN is converges to L1 by definition, for all epsilon positive, there exists, so it's going to choose N1, there exists N1 belong to the set of natural numbers, so that when N is bigger than or equal to that N1, this implies AN minus L1 is less than epsilon. Now, similarly, we're going to use the definition on the second part. If AN approaches to L2, this will also implies by definition for all epsilon positive. So any epsilon positive, there exists N2, must be a different number N2, natural number N, so that when N is bigger than is equal to N1, this implies an minus L2 is also less than epsilon. This is it by definition. Now, if I choose n is equal to the max of n1 and n2, so this will implies when n is bigger than that capital N, which is the maximum of n1, n1. This implies n is a bigger than n1 and n is a bigger than n2. So this is a, we'll say that n is a bigger than n1 and n2. So if n is a bigger than n1, this is also true. But since n is a bigger than, so sorry, this is n2. Since n is also bigger than n2, it means this is a true. So this is basically say these and these two hold when n is bigger than capital N. So therefore, if n is bigger than or equal to capital N, this implies I'm gonna compute the distance between these two real numbers, L1 and L2. Then this we can write L1 minus L2. I'm gonna write a n and also I'm gonna subtract a n. So, and this can be written, basically this interior can be written L1 plus L1 minus an plus an minus L2. So this can be pairing, and therefore this will be less than is equal to, I'm going to use the triangular inequality, this will be less than is equal to L1 minus an plus an minus L2. Since we have the absolute value, I can switch this around. So an minus L1, because if you throw out the negative sign, it will be still same. So, and that's going to be an minus L2. Now we can see that this number, since n is a bigger than capital N, so this one is a less than epsilon coming from here. So this number is a less than epsilon, and this number is also less than epsilon. So we will have this inequality strictly less than basically epsilon plus epsilon, or in other words, this is a 2 epsilon. So what we showed here, so we showed that the distance between L1 minus L2 is always less than 2 epsilon. Since this does not depend on n, it means this is a true for all epsilon. So therefore, since this is a true for all epsilon, I can use my lemma. Therefore, by lemma, this implies L1 is equal to L2. So lemma say that for any given epsilon, if the distance between any two real number is always less than is equal to that epsilon, this time this is a 2 time epsilon, but it's still like a small real number, then L1 and is equal to L2. Or this proves our theorem that if your sequences converges to two different elements, these two different elements must be same, or in other words, the limit of your sequence must be unique. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. So I will see you in the next video.